Hi, I'm Dan Bretsch, and I'm going to show you how you can build your own hydroponic pump system using solar panels, batteries, that's totally off the electrical grid. I've been in electronics since 1958, and I've been in gardening for the past 8 or 9 years, and we're going to show you a complete guide where you can start to finish to do this yourself. I decided to make this video to show you how I've done some of my hydroponics. Some of the new pumps that are out today and the inexpensive prices of solar panels has made this totally feasible to use it off the grid. Why would you want to be off the grid? Well, if you're going to do pumped hydroponics, you have to have the pumps running all the time. And if they stop, there's a total possibility to lose the plants and the structures. So you need to have solar with batteries, and this will totally eliminate this. So that's what we're going to look for. So first of all, the first thing you want to do is figure out how much production you want. Typically, I'd go small in the beginning, and you can always add on down the road. So we're going to look for a small production. What we'll probably do is do 2 pumps, and then we'll go from there and make the system for that, and then you can expand upon that and make it any way you want. So the first thing to know is how many loads are we going to have and for how long? Well, we know the loads are going to be for, I would say, 24 hours, 12 days a week, 7 days a week, 12 hours a day for the pumps, so they need to be on all the time. So then the next thing you know is, my example, I'm going to use 2 pumps. Well, my pumps draw around 13 watts. Now 13 watts at 24 hours is approximately 320 what? Watt hours. So this is the amount of energy you're going to need to run these pumps continuous, all the time. So if we're going to use 2 of these pumps, you're going to have 640 watt hours of energy a day to run the 2 pumps. Now, if you have a timer and turn the pumps off and do an ebb and flow system, you wouldn't need as much. But if you're going to use an NFT system, this would be the way to go. So the first thing we need to do is figure out how much solar panels we need. So the energy that's going to be needed is going to have to run this a day. Now, we're in Texas, and the most predominant thing here in Texas is shade. You can go outside and say, oh, it's sunny outside, but if you see a bunch of clouds, sunny means no clouds. Nothing in the way. No trees, no houses, no structure. So the only way this really works is to have more than enough solar panels to make this work. Over here, this is a typical large-scale solar panel that I'm recommending to use. Okay, this is rated at 270 watts, and I'm recommending 2 of these. And the reason I'm recommending 2 of these is simply because of the amount of shade that's going to be produced in Texas. So let's run the numbers so you can see what I'm talking about. So if we have 270, those are 275 watt panels. Now these panels have standard connectors on the back, and it's just, there's 2 wires. One's positive. I've cut this other one off, and I'll show you why. One's positive and one's negative, and the same way with the other panel. But you have 2 of these at 275 watts, so you're going to have a total power of how much? 550 watts. Well, 550, well, that's great, and we only need 640 watts. Well, if you charge your batteries for 1 hour, you'll almost fill them up for the entire time. The catch is, you only have around 4 to 5 hours a day of sunlight, if the sunlight's there. Why? It's called night. Okay? And when night doesn't produce anything. The other thing, it's about the energy. The energy that you get off the sun only comes in a very short period of time. And you can tell us yourself, in the morning, take a look at the sun and you can see it. Has you ever taken a look at the sun in the middle of the day? You ever just kicked, oh, let me look at the, burn your eyes out. You shouldn't do this. So do not look at the sun with your eyes, but in the morning and the evening people look at the sunset, but there's no energy there for these solar panels. So I only have 5 hours to run this. Okay, so what's the 5 times 550? Well, we have what, about 20? So these are just now arbitrary numbers, but typically you get 250 watt hours to 3,250 watt hours a day. So this is considerably more than we need. But the reality here in Texas, and it really depends on where you are, I'll only get maybe 500 to 600 watt hours a day when it's cloudy. So I've always banked on the worst case scenario. So that's why I've used these large panels. By the way, these large panels were designed for a house. They're fairly inexpensive. I've seen them in San Antonio and Houston for about $100 and $125 a piece. You can get used ones. They have a typical 25-year warranty, 50-year life, so they'll last a long time. So this is where our energy comes from, the sun. Now, batteries. We're going to use batteries to store the energy from. Typical batteries, the old school batteries are the lead acid batteries. Now, lead acid batteries are been around a long time. The newest ones are the lithium ion batteries. You're going to want to use the lead acid batteries simply for the cost. If you can go to Sam's, or you can go to Costco, or you go to Walmart or any retail store and buy trolling motor type batteries. They're deep discharge for between $100 and $125 a piece. If you buy the lithium ions that have the same power output, they're $800 a piece. They're considerably lighter, but we don't care because we're not going to be carrying these things around. And you're going to need 2 of them. 1, 2. Why? Because we're going to build a 24-volt system. And we're building a 24-volt system because the wire size will be smaller and won't lose as much energy in the wires as we construct this device. So we're going to use 2 batteries. They're rated at about 100 amp hours. So each battery would be 2,400 watt. Each group would be 2,400 watt hours. But effectively, you cannot take that battery down that far. You might be able to get 1,500 watt hours out of it, which means you'd have stored energy for about 3 days for this if you didn't have any sun. But again, because the panels are so big, it would charge them up so quickly, even if you got just a little bit of sun. This is the way to go in the long run, so you do not have to worry about where's the energy. Okay, so we're going to use solar panels and batteries for our application. The most important thing between these is coupling these 2 together, and that's called a charge controller. This is a charge controller that's called a maximum power point transfer charge controller, MPPT. Now, you want to use this because it wrangles the last energy out of the solar panels into the batteries, and it's very efficient. It works. These you can get on eBay or Amazon or different places. I'm not getting paid by anybody, so I don't really recommend one. This one is a real maximum power point transfer. The ones are going to cost anywhere between $100 to $150 are the ones you want. And how you can really tell is if they have an input voltage of up to 100 to 150 volts. You do not want to get the ones that are 30 volts. Those are not maximum power transfer devices. These are not $10. These are super efficient. They will also act as a transmission between those photovoltaic panels and that set of batteries down there. Very efficient. So you're going to use a device like this to charge the battery. So all of a sudden, we were going to draw out pictures so you can see how to physically wire this as well. So all of a sudden you've got your solar panels, you have your charge controller, and you have your batteries, okay? So this will set up the system that we're going to use for power. So what we're going to do now is draw up some pictures of how this works. So what we're going to do is take our solar panel, 2 of them, and connect them up in series. There'll be a positive on it, a negative, a positive, and a negative, okay? So we're going to take the negative of one and connect it to the positive of the other. The connectors on the back of the solar panels won't let you connect it any other way, so you don't even have to worry about that. So you're going to come off with a positive and a negative right here. Now, these panels are 35 volts a piece approximately. So you need to be careful. You're really, whether you're going to get shocked or not would be pretty minimal. You need to do, if you choose to do this, you do this at your own risk. But the catch is, the voltage here is pretty small, okay? Now, the wire itself that you use on this is called USE2. If you choose to use this wire is rated for wet weather and sunlight, because you're going to be outside with this. So you might need some USE2 if you really want to do this right. This is also 10 AWG. It's a wire size, okay? So then what you have, once you have these panels lined up, you're going to need to run all this inside where your charge controller is. So let's put our charge controller right here. We're just going to call it CC. You'll take the negative of this and run it over here to the negative of the CC. Really, really easy. One wire over. This ought to be your USE2 wire, because this wire will handle up to about 7 or 8 amps. It'd be fairly powerful. But you don't run this wire directly through it. You put what's called a fuse. And a fuse is a device that limits the energy going through the wire. All it does is really stop a fire. So if you have a fuse here, this fuse is a protection device. It also acts as a switch, and we'll show you some pictures of that too. This fuse should be around 10 amps. Okay? Coming out of this charge controller, you're going to have 2 batteries. Just like I have here. Okay? And we're going to put the batteries in series just like we did here. So you're going to have a positive and a negative, a positive and a negative, and you're going to take the negative and put it to the positive, and out of here you're going to have a negative and you're going to have a positive. This makes it 24 volts, or typically when they're fully charged they'll be 27.6 volts when they're fully charged. So out of the charge controller you're going to take the same wiring, you're going to take your negative out of your charge controller and come over here to the negative of your battery. Straight wire. Now again, this needs to be the larger wire because this device puts out 550 watts and at 24 volts, that's close to 20 amps. So, and that's with full sun when the batteries are really depleted. But you have to work on those cases. So what you're going to do here is we're going to do, positive comes out, but we need to use what? Another fuse. The fuse is for protection from the batteries. Anytime you connect up to a power source like that, you need a protection, a fuse, circuit breaker, some dynamic thing to do that. So then that would connect over to the positive. So what we have is 2 panels, fuse, wire over the charge controller, 2 batteries, and another fuse. This should be 20 amps here. And so therefore, we have between this pole and this pole, this is our power. This is our nominal 24 volts. So this is what our power system should look like. These panels are outside and these should be inside. You can physically put the batteries on the ground and put the charge controller on the wall and put the fuse holders on the wall, however you see fit. But this is our power system. This should deliver enough power to run those 2 pumps 24 hours a day, 7 days a week. It's overkill. Now, if you live in, I guess in New Mexico or Arizona where it's sunny all the time, you might not need both of these panels. But most of the United States, you're going to need them. If you live in Seattle, you probably have to have 4 of these panels because of the tremendous amount of weather they have up there. Of course, if you live in the eastern part of Washington State, it might be nicer. But it all depends on your choice of where you're going to be, where you're going to do this. So next up, we're going to move on to the actual pumping. We're going to talk about pumps right now. This is the typical pump that I recommend. The reason I recommend a pump like this, although it's very small, is because it's called a wet rotor pump. It has no bearings in it that are going to wear out. It has no seals that are going to be any problem. And it works directly on DC, so we don't have to have any inverters from the the DC voltage to the pump. Anytime you go through an inverter, you're going to have efficiency loss. By using a motor that's directly connected to the pump, you don't have that lost. This motor itself is rated at 12 volts DC up to about 6 meters. We only need about 3.5, 4 feet of lift, so that's plenty. It also runs a tremendous amount of liquid through it. So if I turn on a little power supply over here, this is the little pump running at 13 watts right now, running this much water. And you put your nutrient in there, you're in great shape, and that is a lot of flow. So what I typically do is slow mine down a little bit, around 10 volts, and the reason I run 10 volts in it is because it gives the semiconductors less current to go through it. Although the energy of the water is a little bit less, it's not that much. The problem you have with almost any piece of equipment like this is called infant mortality. Infant mortality is a piece of equipment that goes dead way too fast. A pump like this, they cost about $13 to $15. It will typically last 50,000 hours, but you might have a situation where the pump goes dead in a couple of weeks. That's called infant mortality. If it's on for more than a month, you're usually good to go until whatever. And it's very simple on the inside. If you have a pump on the inside, what it looks like is this. This is the rotor that's on the end. Now see, I left this in the nutrient way too long, for about a year, and I never turned it on, so it precipitated out. But this is all it is. This is a magnet running around inside the magnetic field here. The only thing I do not like about any of these pumps is the wire length is so short. It makes it you have to put wire on this. But if you're going to submerge, because this is totally submersible, you have to put wire on it. Well, I'll solder it on there, but I'll also put caulk over it, and then I'll put my heat shrink around that and put it together. So this is the type of pump I recommend. We need to talk about soldering. Soldering is a crucial aspect of this so that you can get the wires on correctly. I have a piece of wire here. This is probably 22, 24 gauge wire. And I'm going to be using the two conductors, one for positive and one for negative, for the system. Now you can strip this wire. Old guys like me will take a pair of dikes or wire cutters and just pull it off like that. If you're uncomfortable with that, you can get yourself a pair of wire strippers and just strip it off like that. Once you have that, you're ready to start soldering. Well, the catch is, to solder this right though, you're going to need to tin this. And tinning this is a process of taking solder like this and putting it on the ends of this wire. Now, did you notice what I just did? I just took my soldering iron and just unconsciously wiped it on this sponge that has water. That keeps the tip clean. Cleanliness is next to godliness in soldering. If you don't have a sponge, get a paper towel, wipe it down, and then tin this. Once this is tinned, and this is a soldering station, but you don't need this. You can get a regular soldering iron and do this, but you keep it clean. So you'll come up here with your solder and your iron, and you'll put it on your wire like this, and you'll tin your wire. Okay? So we're going to tin both pieces of wire here, one positive and one negative. Okay? But if you look at this wire, well, it's just way too long. So what you do is you're going to trim it up. You're going to dress it out by taking your wire cutters, and we don't need very much, so I'm cutting it off way back. So all of a sudden now you have a clean solder and you have your insulation up to it. Now we're going to be using what's called a buck converter to change that 24 volts down to 12. Why we need that is those pumps draw 12 volts. And this is the buck converter. Well, why are we using this in the first place? Well, wire runs from your battery to your pump can be fairly long. It might be, 100 feet, 150 feet. You're going to lose energy in the wire. So if you run it to higher voltage, the buck converter will take and reduce the voltage at the device what you want to be. So at this point, I'm going to want this to be around 10 volts. All right? So the high voltage, the 24 volts, will come in here and come out here. So what you'll do, and this little buck converter, what are they, $2 or $3? They're not much money at all. It has a little adjustment knob. This little blue one is a 20-turn knob that adjusts the voltage. You will have to learn how to use a simple voltmeter. And the voltmeter itself can be picked up almost any place. You can get the least expensive one, $5, $6. It's not a big deal, okay? It'll help you know your deal. So if we connect this, and I like using this tool here to hold it so it doesn't chasing it all over. Unless you have somebody to help hold it, a tool helps out. So the first thing you do on this is you're going to tin up your sides where you're going to put this wire on. You want to be sure it has solder on there, cleaning as you go. And then what we're going to do is connect this. I use the orange wire as positive, and it could be red, yellow, green, it doesn't make any difference. And I always use black as negative. But it's not mandatory, anything you feel comfortable with. So there's one on there. And here's one. Whoops. Oh, darn. There we go. So now what we have is two good connections. One negative, one positive, one negative, one positive. And this is what's called a buck converter. It'll take the 24, 27, up to 30 volts and change it down. Okay? So that's what we need. Now, to make it work right, we have to adjust the little knob here on the top. So you need a little screwdriver. Okay? This little screwdriver will do this. So what we'll do is turn it on. And let's see, this is too low in the first place. There's our 24 volts coming in. You notice a little red light coming out here. Most of these devices have some to indicate that power is there. So what I'll do is I'll turn my voltmeter on and connect it up. And I'll use these alligator clips. And the alligator clips will allow me to have a free hand instead of trying to hold 4 wires with one person. So I take this, and I'll connect it up over here. And I'll connect the green to ground, which is negative, black. The orange comes over here. And I'll turn my voltmeter on. Well, the voltmeter is real close to the 10 volts. Now that's typically not the way these come. You have to adjust it down to where it goes to. So what you're going to do is adjust this with this little screwdriver, this little potentiometer. You see it going up and down there? So this adjusts it to the voltage that you want to set up for your piece of equipment. And since we're going to be using a pump, I usually set mine at about 10 volts. And right now it's at what, about 10 volts. So it's adjustable right from here. So you'll see that if we take this meter, has the 10 volts coming out, and if we put it here now, we have the 24 volts coming in, right? So we're in good shape on that. So this is our buck converter that we're going to use. This is good for around 3 amps, but I use one per pump at the actual site. So what'll happen is I'll take this buck converter and I'll connect this wire to the pump, and I will only have around 5-6 feet of wire. And I've being the cheap person, I've used network wire to go from here, the higher voltage, all the way back to the 24 volts. You're going to lose a couple of volts in the network wire. Who cares? Your pump's still going to work out just fine the way it is. Fuses. Okay? We're going to talk about fuses now. A fuse, and this is old school fuse, okay? This is an old school fuse. It's really big. This is called a 3AG, and this has been standard around for a long time. There's also these GMA fuses that look small like this, and you can get fuses that are the automotive type fuses with the spade on them, okay? This is a fuse holder. This makes it real easy. A fuse holder like this or a fuse holder like this makes it real easy to work with. Also, there's the clip encapsulated fuse holders. So you'll find a fuse holder like this where you just twist it, there's your fuse. It's right there inside of the whole thing. Now, the wire size of these fuses needs to be handling the current on the system. So you'll see that the wire size of the fuse for the solar panels and the batteries to that situation needs to be fairly big and heavy. Whereas from the batteries to the pumps, you're going to put a 2 amp fuse, 2 or 3 amp fuse in it. It's not very big at all. You'll be using small wire anyway. So you can either get one like this that has outputs, when it has tabs. All these fuse and fuse holders are on eBay and Amazon, all over. We go to your local Radio Shack store if you have a Radio Shack store. So the fuse holders work out real nice that way. Now, let's presume you want to do an ebb and flow system, where you're going to need a timer. And this is a 12-volt DC timer that I picked up again on the internet. And it's really nice. It will do up to 17 different times. I mean, you want to choose the day, the date, you know, Monday through Sunday. You want to 17 different times, long as you want. It's all digital, and they're only between $10 to $15 type of thing. They work on 12 volts DC, and there's a switch on the outside. The switch is just like a ordinary house switch. So you would put this in series with your controller here. So you would break one of these wires, put a switch on there, and it goes off and on depending on the time. But you also need to have one of these buck controllers to lower the voltage to run the timer. So you need to set that at 12 volts. So that's actually pretty straightforward if you're going to do an ebb and flow system. Ebb and flow systems, again, with the pump, with the water system, however you want to do it is great. That's straightforward there. But you wouldn't need a fuse between here and here if you're going to have your 12 volts into this. It's not a big deal. So you would get two or three of these. I would get, I mean, at $2 or $3 a piece, you could get half a dozen of them and have some in reserve. On the pumps, typically what I do, if I'm going to have 2 pumps, I'll have 3 just in case I lose one. So what we're going to do is complete the actual schematic drawing of this so you can see how this would wire together. We already have our 24 volts over here. So what we'll do is we'll take our negative, and like I said, I like to use network wire because it's cheap. And it's perfectly fine for this low voltage DC. So the network wire would come over here, and the first place we're going to come to is what? It's going to come to our little block we call the our DC to DC converter. Okay, this will be the DC to DC. The negative will go to the negative, and the positive will come out here, come around, and go through a fuse to the positive. So positive to positive and negative to negative over here. This is probably a 2 amp fuse. And this is going bad. Okay? But coming out of this goes directly to the pump. So this goes directly to your pump, to your system. So anytime you would put the fuse in the system here, the pump would come on. You would have your 24 volts out here to run the system. Now if you wanted to have an ebb and flow system, you would take this same 24 volts, come out here to a, let's see, let's come down here. You'd have your 24 volts, you'd have negative and positive, and you come out to a one of your little modules that changes DC to DC, and you're going to have your set one up for 12 volts. Okay, and that will run the little timer. Okay, so you put the 12 volts into the timer, the negative to negative, positive to positive. Some of the timers are AC, so it won't make any difference which way you put them in. But there'll be a switch on this timer. And it'll tell you definitively on the back of the timer where the switch is and where the power goes. So at this point, you would also take this and run a wire from the positive to one side of the switch. Then you have the other side of the switch here. And then it would be the same thing as up here. You would run another module, negative, positive, or no, positive here, I got that screwed up, positive on the top, negative on the bottom, and then this would come around all the way up to our negative system here, and then coming out of this would be another pump. Okay? And this would be your positive and negative here, and your pump here would be like this pump here, although you would have a timer to turn it off and on. Alright guys, I'm new at this, so this is the first time I've done this, and if there are any comments, I'll try to answer them. This has worked for me in my greenhouses, and it's been a pleasure doing it. And I thought I'd try to express how inexpensive and efficient these little pumps are instead of getting an AC pump. An AC pump, you change the DC voltage to AC, you're going to lose 25 points there, 15, and then by the time you come back to the pump, you're losing energy there. Why not just run it directly to the pump? That's why I use DC. Thank you.